All right, good, thank you. Okay, so let me just pick on a few of the points that the previous speaker, Johannes, introduced, and let me discuss them perhaps in more detail. Okay, so we know that the properties of strongly interacting systems are dictated by QCD, and there's some parts of QCD we know quite well. We know that the symptotic freedom actually helps us making perturbative calculation work at high energies, and at lower energies, the coupling actually grows, and then we require non-perturbative methods. Lattice QCD is one of them. The other thing we know quite well is how this runs, and so we can actually determine the QCD coupling at some fixed scale. So here at the mass of the Z, it's tabulated, and here it is, and the error is actually quite small. And we heard several talks in this meeting how to make this, perhaps to narrow down those error bars a bit more, and here's a tabulation of jet-related measurements. Okay, so there are some parts of QCD that are known quite well. There are parts of QCD that are a little bit less known. QCD, first of all, is a concise Lagrangian. It's remarkably simple when you write it down, but yet it yields a large spectrum of phenomenology. It's quite rich. For example, we know that the QCD vacuum is characterized by some condensates, and those condensates are requirements of chiral symmetry being broken by the ground state. So as temperature increases, we do know also that that symmetry will be restored, and these condensates will melt. So it's a fundamental question in QCD, well, how does this melting go? So this is something we'd like to investigate. The other thing we also know is that the constituent mass of most of the quarks around us actually are only partly due to the Higgs mechanism. It's mostly due to the interaction with the QCD condensate. So this is quite relevant. So the related question is, what is the bulk behavior of QCD? What are the collective features of QCD? Another way to say this is, what is the phase diagram of QCD? This is perhaps a little less known. Well, okay, so how do we investigate this? Well, theoretically, there are a couple of ways, and I'll discuss those in a minute, but in practice, in experiment, the only practical way we know to do this in the lab is to collide large nuclei, to heat and compress nuclear matter. So here's a simulation from the Madai group in the US, which is a consortium of Michigan State and Duke University. And on the right-hand side, you have a phase diagram, most of which we don't know very well. So temperature plotted against baryon and chemical potential, which is a surrogate for baryon density. Some parts of this we know actually quite well. For example, I'm going to tell you in just a minute that this temperature here is pretty well known using perturbative QCD techniques. The other thing we know quite well is that this part of the phase diagram is not a proper phase transition per se. It is a rapid crossover, okay, from different degrees of freedom here and different degrees of freedom there. This part down here at low temperature and at nuclear matter density, we know quite well. And there are also a bunch of effective theories that tell us that this line is a first order phase transition between these degrees of freedom and those degrees of freedom over here. So if this is true, putting all of this together, this is a crossover, not a phase transition. A phase transition here needs to be a critical endpoint, and there's an experimental program to look at this at RIC, and also this will be a part of the program at the future FAIR collider in Darmstadt in Germany. Okay, so fine. So this is how we investigate the phase diagram experimentally, but this also implies that there's a time-dependent sampling of the phase diagram. You can't do this without some model that'll tell you how the collision evolves. Because you're colliding heavy ions, the density changes with time, the temperature changes with time. So you're actually spanning a region of this phase diagram. Okay, so what is known from lattice QCD? Well, okay, a couple of years ago, there was some discrepancy between two major collaborations in finite temperature QCD on the lattice. They would find different critical temperatures. This discrepancy has been resolved. because it is known, for example, this is a picture from the hot QCD collaboration, that if you use different effective actions, different discretization procedures, taking the continuum limit over here is a little tricky. So you can have different actions that give you different temperatures, and yet they can still yield the same critical temperature taken to the continuum limit. So the two collaborations, hot QCD and the Wuppertal-Budapest collaboration, they did use different effective actions. And now this discrepancy, which was a problem in this field for some time, is past. It's been resolved, and this was reported at Quark Matter recently. And this is the result, for example, of the trace anomaly as a function of temperature by these two groups. And this agreement extends to the main thermodynamic variables. For example, you see the pressure scaled with density here, with temperature rather, and the effective energy density, entropy, and speed of sound calculated in those two approaches by these two collaborations, and they agree. So the equation of state from lattice QCD at 0 baryon density is known. It's not a problem anymore. And this is one of the ingredients we need to explore the phase diagram. I'll tell you in just a second. Suppose you want to go away from this point over here. So suppose you want to move away. Okay, so in lattice QCD, this is a bit of a challenge because as you move away, the QCD action, when you have a finite chemical potential, the QCD action becomes complex. This is not a problem in itself, but the problem is that you use this as a measure to do Monte Carlo calculations, so probabilistic techniques are no longer possible. So you have to do some tricks, and there are a variety of tricks people have tried. So going to imaginary chemical potentials is one of them, and then doing analytic continuation back to chemical potentials. There's some reweighting techniques. And there's a Taylor expansion, and this is what is Krebs over here. So suppose you want to Taylor expand the pressure as a function of the chemical potential, or chemical potentials, depending on what quantity you have that are conserved. The expansion coefficient, you can actually calculate because those are evaluated at 0 temperature. So these are the generalized susceptibilities, and there's been some progress in doing this. Okay, so it's been estimated, for example, that the order mu beta to 4 will become important when you go to collisions that are 20 GeV per nucleon, and then you have to go over to mu beta to 6 when the collision energy is even lower. Okay, at LHC energies, we're lucky because mu b is essentially 0. So then the lattice equation of state that mu b is equal to 0 is actually good. But this is a hot topic in the field, and there's some steady progress in this area. Okay, so the question is, okay, phase diagram. Is there collectivity? Can we talk even of temperature in heavy ion collisions? Well, okay, so now we have standard picture. I'm careful not to say model. It's a standard picture of high energy heavy ion collisions, which you've seen earlier. So initial state, okay, Lorentz contracted nuclide. There's a pre-equilibrium phase, also called the Glasma phase. There's a quark-gluon plasma phase, hadronization, and thermal freeze-out, where the particles essentially have a mean free path that is longer than the interaction length. All of this goes on in just about 20 Fermi over Cs, or 20 or 30 Fermis over C. So this is quite fast, but it's not that fast on the scale of the strong interaction. And this part here turns out to be describable surprisingly well by relativistic hydrodynamics, and this is what the part that I'll talk about now. So if you look at the program, you'll see a large part of the program devoted to heavy ion collisions that is devoted to soft observables. Why is that? Well, it is because hydro actually works quite well. If you look at the stress energy tensor, for the ideal stress energy tensor, so this is the energy density, this is the pressure, and this is flow velocity. So this is the most general form it can take. And the equation of motion for this stress energy tensor is this. And if you supplement this with lattice QCD equation of state, then you have a hydro model. Okay, so if you don't have this to close this set of equations, you have too many equations and too few. You have too many equations for variables you have, and this permits you to close the set of equations. So the lattice QCD equation of state is an ingredient that is vital for this approach to work. And on this figure, you have a plot of spectra measured by the Phoenix collaboration at Rick, using measured by the Phoenix collaboration for different centralities. So there's a measure of the head-on, this is head-on collision, and this is more peripheral collisions. And this is a calculation here using a 3D relativistic hydro, which for the moment is ideal. So this is using this with zero viscosity. You've just seen this picture shown by the previous speaker. And again, this is this data again. And this is the spectrum reported by Alice and lead on lead at DLHC. And there again, you see that the hydro works quite well to explain the spectra. Let's see if we can go dig in a bit more, go past the spectrum. Well, okay, so one way to do this is what Johannes described, is to say, okay, let me take this, this triple differential spectrum, and let me expand in terms of the azimuthal angle. Okay, for example, you can think of the collision as this nucleus going in the board and this coming out. Okay, there's an overlap region, and if you look at the angle around this, it's the azimuthal angle, and this is a reference angle provided by the participants. I'm defining this as the participant angle, and you can actually calculate it. And then these coefficients here will tell you the strength of these different harmonics. Okay, so 1 is called the directed flow, 2 is the elliptic flow, 3 is the triangular flow, and so on. Okay. One way to understand this is to say, okay, so you have this hot region that is quite hot and dense. There's some pressure in here. And if you look at the Euler equation, it tells you that the force is actually related to the pressure gradient. So the pressure gradient in this direction is actually larger than the pressure gradient in that direction. So particles should expand more in this direction than they will in that direction. Okay? This is what drives the expansion. So another way to think about this is that the anisotropy in coordinate space, so this ellipticity, which you can calculate, is actually related to the anisotropy in momentum space. One translates into the other through the hydro response. So these harmonics go up to values that are measured, and I'll tell you in just a second how they're measured. And they look like this, okay? And the state of the art currently includes deviations from thermal equilibrium. The viscosity is one way to characterize this deviation. It includes fluctuation of the initial state, event by event. And so different initial state will give you different fluctuations, and we'll see if we can identify those. And one thing is that it doesn't really explain thermalization. Okay, you have to put in thermalization by hand. But this is rapidly changing because some recent calculations actually show that you can actually thermalize if you start with an initial state that I'll describe in just a second. So in other words, there's some hope that we'll be able to thermalize right from the get-go with these intense gluon fields. So perhaps that was a question that was asked earlier. So can you calculate from zero, can you calculate thermalization? And the answer is not yet. But we're getting there. There's an analogy with cosmology. You've seen this picture earlier in this conference. So this is the WMAP picture of temperature fluctuation. And you can actually quantify this by looking at the angular distribution, which goes up to a staggering multiple moment of 2,500. In nuclear collisions, you have several of those. Okay, so several initial states. You can actually characterize those by going through the hydro evolution. So you start with one of those, you evolve the hydro, and then you analyze the initial states and these multipolar moments in this expansion of the azimuthal spectrum. So there's some analogy between this and that. Here this goes to 2,500, and this perhaps goes to a more modest 7. So the cosmology of heavy ion, I'll let you read this, and I'll go on. So it's actually quite similar in some sense. Okay, so viscous hydrodynamics, this is one of the breakthroughs maybe of 10 years ago. So you can actually go from ideal to viscous, and the first order correction to viscous hydrodynamics gives you the Navier-Stokes equation, which is acausal. So there's a problem, and this was solved some years ago in the astrophysical context by those people going to second order. and introducing a transport coefficient that tells you how fast your solution for the shear pressure tensor relaxes to the Navier-Stokes value. So this is a transport coefficient that screens you from these acausalities. So eta is the shear viscosity, and it measures the resistance to deformation, and it is a fundamental property of QCD. So it's out of equilibrium field theory, and the field theory here is QCD. So shear viscosity is a transport coefficient. It is a fundamental property. Can't we just calculate it? Well, okay, so this shear viscosity admits a Kubo relation. So this is the traceless part of the stress energy tensor. And you can try and calculate this. Okay, so for finite temperature QCD, it has been calculated perturbatively. And I'll show you what it gives in just a second. It has been attempted on the lattice by these people here and others. And I say lattice with an asterisk here because it's a little tricky to do these correlators on the lattice at finite temperature because you're trying to get to a spectral density, okay, which is related to this. And the spectral density is integrated over, and it's integrated over multiplied by some kernel, which is oscillating, and it's a function of temperature. And what's on the left-hand side is what you're measuring. So you're trying to get to the spectral density by inverting this kernel, and the left-hand side is typically noisy, so it's a bit of a challenge. But very interestingly, you can do a calculation like this using strong coupling techniques, string theory techniques, ADS-CFT, and this was a breakthrough by these people here. It actually was a bomb in the field because if you calculate this, you get eta over S that is for conformal field theory, it is identically 1 over 4 pi. So it's very interesting because we'll see in just a second, because this low value is the lowest value of any substance we know of. And the other thing is, it's a low value like this that is needed by simulations of nuclear collisions. Of course, QCD is not C, it is not conformal, but I'll come to that in just a second also. So what do we know? Well, we know the following. On the right-hand side, here's eta over S as a function of temperature. Here's the perturbative calculation, okay, which breaks down over here. So it's good at in the high temperature limit. Here's a calculation using pions. So it is a chiral Lagrangian on the left-hand side. Here's the chiral Lagrangian answer. And again, it fails around TC. So this is good over here. And here's this KSS bound by these people that did the CFT calculation. And you see that there's a hint of this coming down, this going up, and a minimum perhaps over here. If you do the lattice estimates, you get things that are with a large error bars, but are pretty close to the KSS bound. And these calculations are upper bounds by this calculation over here. So to sum this up, the theory constraints are not that strict. They're pretty loose. Can we actually measure this? Okay, so let's turn on this hydro machinery. And let's do these measurements of up to n is equal to as high as we can measure them. And the first thing we will comment on, if you do a hydro calculation, it turns out that the higher harmonics are more sensitive to the viscous corrections. And this is very sensible because the higher harmonics will tell you about smaller inhomogeneities. And as you turn on the viscosity, those are the first ones to disappear. So it makes eminent sense that the higher you are in the harmonics, the more sensitive it is to viscosity. And here's a plot of the Phoenix measurements at TRIC up to V4. And you see the sensitivity here varying eta over S. So there's a sensitivity that you can actually discriminate with the data at hand. I'm not saying that this is the value you should actually use because there's there's a subtlety I haven't discussed yet that's not in these calculations. Oh boy, okay. Yes. So let's stare at this as long as it took me to make this. Okay, so here's a simulation using this three-dimensional hydro we call MUSIC. It's an acronym. Okay, so what I'm arguing here is that event-by-event fluctuations are important. And this thing I drew earlier, this area here was smooth. And if the area is completely smooth, and there's some reflection symmetry you can show, there's symmetry that tells you that all the odd moments, all the VNs that are odd, V3, V5, should disappear. And you need this. Why do you need this? Because, for example, you calculate different V2 and V3 over here. And we calculated, back in those days, V2 for different centralities using an initial state that was not smooth. It was already known then that you needed a non-smooth initial state, and then made a prediction for V3. And this prediction is the red curve here with the same value of viscosity on the left-hand side. And this is the Phoenix measurement after the prediction. So these fluctuations actually were actually reasonable. The other thing I'd like to draw your attention to is that if you start with the initial state at, say, 0.4, here's the same state evolved to 0.6 in the ideal case, and here's the same state evolved to 6, rather. Here's the same state evolved to 6 in the viscous case. And you can see by eye that the viscosity will smooth out the bumpy initial state. All right, so how do you calculate this? The way to do it at the moment is a framework that you probably have heard of called a color glass condensate. If you take a nucleus and you Lorentz boost it at some very high energy, the fluctuations will appear frozen and the wee partons will actually show. And the more energy you have, the more of them will show up. And at some energy, there's some saturation phenomena that is bound to set in. Okay? So one of the goals of this field is to explore the region where the saturation phenomena sets in. So the saturation regime is characterized by a scale, and in this regime, the occupation numbers are actually very high, okay, because they go like 1 over alpha s. So there's strong fields with large occupation numbers, so a classical description is actually sensible. And so this CGC is an effective theory of QCD for these very high energy collisions that probe very low X. Okay, so what is done is to say, okay, let me try and calculate the initial state using CGC techniques. This is done, and this is described in this slide, so let me just summarize this by saying that we use a model that's been tested at HERA, where again, deep inelastic scattering will reveal these color fields. These color fields are evolved using Yang-Mills equations, classical Yang-Mills equations, because they're classical fields. We can actually calculate the stress energy tensor and then feed it in the hydro. So this is now our initial state. So this is the summary of this curve. So this gives you an initial state like this. And if you just sample the nucleons just by saying, okay, you have straight-on collisions of the nucleon, and the nucleons will fluctuate. There'll be fluctuations because the nucleons will fluctuate, their position will fluctuate in the nucleus. This is what I call here Monte Carlo Glauber. So this also is an ingredient to that, but on top here, there's another source of fluctuation. For example, so the nucleons here are also allowed to fluctuate, but the color fields are allowed to fluctuate in the nucleon. So this is an initial source of fluctuation. We've identified a variable that's sensitive to the initial state. It is Vn divided by the average Vn, and I can explain to you why that's the case. But let's first make sure that our average Vn we calculate is comparable to what's measured experimentally. So this is a set of measurements by Alice and by Atlas. And again, with the same value of viscosity, which we take here to be a constant, we can actually go up to a very high value of V4, and we make a prediction for Vn. So the average part is under control. And what's revealing is the distribution, and this is the distribution measured by Atlas. Okay, and if you calculate this and you compare against the Atlas measurements, you get this remarkable agreement. Okay, and the other thing you notice is that you can actually calculate Vn and divided by the average and compare against the Atlas measurement, and you can actually calculate the initial eccentricity. Which is not measured, of course, but you can calculate it in the model and do the same, initial eccentricity divided by the average, and they agree. So this is a proof that actually Vn over V average is a reflection of the initial state in coordinate space. This is for V2, V3, and V4. V4, the agreement with epsilon and V is not as striking. There's some slight hydro response that is needed. But once you do the hydro response, what you calculate is exactly what is measured by Atlas. Okay? So the initial state we calculate has something to do with what is actually going on. And with all these bells and whistles, this is what we can say. At RIC, eta over S is roughly this value, and at LHC, it is roughly that. I say roughly because I would say this statistical error here is something like 20%. There's a systematic error that I'll discuss in a second if I have time. So that's as good as we know it for the moment. It indicates there's a temperature dependence, perhaps, because LHC is a higher temperature than RIC. But this is the state of the art. How well do we know the temperature? Well, Johannes alluded to this. Does it make any sense to talk about temperature? Is the system thermalized? This hydro analysis would argue that yes. Can we actually measure it independently? And we can actually do this by photons, and there's the technology to do it. But then with all the things I've told you, let me just quickly do this in a jiffy. This is the temperature measurement done by Phoenix, and this is the temperature measurement done by Alice. So 220 MeV, 300 MeV for Phoenix, and 300 MeV for Alice at DLHC. You have to be careful because when you do this, you have to realize that the temperature you measure is an effective temperature. I've argued that the hydro is wonderful and it does many, many things very well, but the hydro also tells you the system expands very fast. So this is bound to contaminate the temperature spectrum because those photon sources will be blue shifted by the expansion. And this is not an invariant spectrum, so the blue shift will matter. So you need a hydro model to calculate this, and this is what I'm saying, and this is what I'm explaining here. And what I'm saying is that if you have a source that's moving with a certain velocity, there's a Doppler shift that comes in and tells you that the true temperature is not what is measured by the slope of the photon spectrum. So you actually need a hydro calculation, and here's a calculation. Temperature against proper time in each of the fluid cells. So there's the distribution, okay, because there are many fluid cells, and this is how the temperature evolves as a function of the proper time. If you look at the effective temperature, what you would measure from the slope, you would get this. Okay, so you get a hardening of the temperature because of the blue shift, and this is what is actually measured by RIC. And the size of the arrow is actually the error bars. So there's some consistency with this and the realistic hydro calculation. And the same is true for Phoenix, for Alice at the LHC. So the true temperature is a function of the proper time, and here's the effective temperature, and this is the measurement. Okay? So it tells you that these photons can actually be used as thermometers. They actually worked. T above TC is actually reached. There's no question about this. Okay, so you look at temperature above 250 MeV, for example. At LHC, there's more than a third of the photons that come from that temperature. But to actually fish it out, you need a model to do this. And the hydro is a model that does that. Let me just talk about V3. V3 is measured in proton-lead collision. And the surprise there is it was as big as it is in nucleus-nucleus collision. And first, people looked at this and it says, this can't be. You can't have hydro in such a small system. And then you ask yourself, why not? Well, let's do a calculation. One way to characterize the hydro is the Knudsen number. And if we do a calculation for the Knudsen number of the proton-lead spectrum, okay, you turn this around. You say, okay, let's put the Knudsen number to be 0.5. Anything above this is not good hydro. Anything below this is pretty good hydro. And if you look at the maximum eta over S that's allowed by the high multiplicity proton-lead data in the inset here, it's actually just above this 1 over 4 pi, which is something that's common in these calculations. So I'm saying that PA is actually closer to the gray zone, but it's tenable in the high multiplicity region. So actually, hydro might very well make sense for proton-lead collisions. Okay, so let me just skip the jet part, and let me get to the conclusion. I've argued that high-energy collisions are telling us about the initial state through the QCD nature of the nuclear wave function. So there's a direct connection with QCD. It tells us about the property of strongly coupled medium. So eta over S is measured now to some degree of precision that's actually quite nice. The equation of QCD, EOS of QCD, is a required ingredient, so there's another collection. connection rather. The fluid dynamical paradigm, part of the standard picture, is still evolving. Okay, there's still bells and whistles we're bringing to the hydro, but this revolution, I would say, is not over. I would say over 5 to 10 years ago, the hydro we had is quite different from the hydro we have now. So there's been literally a hydro revolution. And Rick and LHC are working together. The data we get from one complements the data we get from the other. So it's actually quite crucial. And you can read the rest, and I thank you.
So it's quite late, but we have time for an urgent question. Well, I don't see any questions, so we should thank Charles again. And we should come back at 11:30.